Okay, welcome back to another video on the Maths channel. It's your teacher, Mr. Lim here, and in this video, we are going to be looking at minimum spanning trees. This is part of the Year 12 standard course. By the end of this lesson, you'll be able to define what a tree is, explain what a minimum spanning tree is, and identify the minimum spanning tree from a weighted network diagram. So let's first start off with part 1 of this lesson. What is a tree? A tree is a connected graph that contains no cycles, multiple edges, or loops. A spanning tree connects all the vertices of a graph, and if it has n vertices, it'll have n-1 edges. So if it has 10 vertices or 10 nodes, it'll have 9 edges. If it has 27 vertices, it'll have 26 edges. So we can see here, graph 1, that's considered a tree. Graph 2 is also a tree. However, graph 3 is not a tree. And the reason why it isn't is because it has a loop, a cycle, and it also has multiple edges. So basically, if there is a closed area that you can color in, like so, it is not a tree. Okay? Whereas the other ones here, there's no area that you can color in, so it is a tree. Okay? When we're talking about spanning trees, it connects all the vertices of the graph. Now I said that spanning trees will, if it has n vertices, or have n-1 edges. So let's just double check that. Let's see how many vertices graph 1 has. 1, 2, 3, 4, 5, 6, 7, 8. So it has 8 vertices, so it should have 7 edges. 1, 2, 3, 4, 5, 6, 7. Good. So we know that this is a spanning tree. What about graph 2? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 vertices. So in order for this to be a spanning tree, it needs to have 10 edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So that's a spanning tree. Alright, let's just get rid of all of that. So what is a minimum spanning tree then? Well, a minimum spanning tree is a weighted tree that connects every vertex and has the smallest possible sum. So we can see here in this diagram, we can create lots of different trees, right? As long as that the whole thing is connected, all the vertices are connected. So let's see how many vertices there are. 1, 2, 3, 4, 5, and 6. There are 6 vertices. So for a spanning tree, there needs to be 5 edges. So as long as there's 5 edges and all the nodes or vertices are connected, then it's a spanning tree. So I could draw something like this. 1, 2, 3, 4, and 5. That is a spanning tree. Right? So I'll just draw that out. Okay, that could be a spanning tree. All the vertices are connected. Or I could have drawn this one. 1, 2, 3, 4, and 5. That's also a spanning tree, right? Because all of the vertices are connected. Okay, and there's no areas that I can color in. There's no closed areas. 6 vertices, 5 edges. Or I could make another one. What if I highlighted 1, 2, 3, 4, and 5? 1, 2, 3, 4, and 5. Okay. Lots of different spanning trees in this weighted network diagram, but the minimum spanning tree is the one which has the smallest possible sum. So if I were to add these numbers, what number would I get? Okay, so here we've got 5 plus 6 plus 3 plus 5 plus 2. 10, 19, that's 21. Okay, that has a weight of 21. This one here, that's 6, 6, 3, 7, and 6. what's that? 18, 25, that has a weight of 28. So that's definitely bigger than 21. And this one here, that's 2, 8, 5, 2, and 7. 10, 19, 24. So it looks like this one's the smallest so far. But is there one that's actually smaller than 21? Okay, I will go through how to do that with you in the next part of this video. But before I do that, I just want to go through why. Why do we need to learn about minimum spanning trees? Well, the main reason why people use minimum spanning trees in real life is to minimize cost, right? Let's say we've got a business who has been tasked to connect 6 different towns. Okay, as long as you can get to each town, doesn't matter how long it takes, as long as you can get to every town, then it's all good. And let's say we've got these 6 towns here, A, B, C, D, E, and F. Well, the business that has been tasked with this project might be thinking, okay, well, how can I minimize cost? What is the least number of kilometers of road that I actually need to lay down? And they might be like, okay, well, maybe it will be this one. I've connected every single town. I can get from B to F. It will just take a really long time because I have to go through A, D, C, and E. But I can get there. And with this, we've got 2 plus 5, 7, 10, 15, 17. They only need to lay down 17 kilometers worth of road, which will save them money. Of course, it won't save money for all the people who have to drive from B to F, for example, but it will save that business money. Okay, so that's one of the main reasons why we need to learn about minimum spanning trees, usually to save cost. So, exactly how do we identify the minimum spanning tree from a weighted network diagram? Well, here's some steps that I've created that will help you out. Count the number of vertices. There needs to be one less edge. Remember, it's a minimum spanning tree. The second step is to highlight the smallest edge, and then keep highlighting the next smallest edge unless if it creates a closed area. And I want you to keep doing this until all the vertices are connected, and double check that you have one less edge than there are vertices. So here's this question that we just looked at. So we'll count the edges. 1, 2, 3, 4, vertices. 5, 6. So there are 6 vertices. So we want 5 edges. Okay, so I'm going to highlight the smallest one, smallest edge. The next smallest edge, that's fine because it doesn't create a closed area for me to be able to color in. 3's next, 5's next, 5's next. And you can see that every vertex is now connected. So 1, 2, 3, 4, 5, there are 5 edges. Now, typically in an exam, you'll be asked to draw that minimum spanning tree. So when you draw it, make sure you draw it nice and neatly, follow it exactly how it looks. Label all the vertices. And the weights. 2, 5, 3, 5, and 2. And then a typical question would ask you to calculate what the minimum weight is. So the minimum weight, we just add those numbers together, and we calculated already before. That's 17. So I'm going to do one more with you, and then I'll get you to pause the video and have a go with C and D, and then you can check your answers. So how many vertices are there? 1, 2, 3, 4, 5, 6. There are 6 vertices, so I need 5 edges. Alright. The smallest number I can see is 3. The next smallest is 3. Next smallest is 4. Next smallest is 5. Can you see how so far I have not created an area that I can color in? If I said the next smallest is 6, and then I highlight that, oh no, I've got this area that I can color in. I've created a closed area. So I can't highlight that 6. The next smallest number is 7. I can highlight that because it does not create a closed area. Now every vertex is linked, is connected. Let's just make sure I do have 5 edges. 1, 2, 3, 4, 5. Good and done. So I'm just going to draw this for you. So we've got F, E, D, C, B, and A. 4, 3, 5, 3, and 7. And so here we can see that the minimum weight is 10, 15, 18, 22. Alright, I hope that makes sense. I've got plenty of examples for you to try. I don't expect you to be drawing the actual minimum spanning tree out. Just highlight it and tell me what the minimum weight is. Okay, pause the video, have a go with C, D, E, and F. Alright, welcome back. Let's check our answers. So here we've got 1, 2, 3, 4, 5, 6, 7, 8 vertices. So I really should be highlighting 7 edges. So let's highlight. 2 is the smallest. Then 6. No, not 6, sorry. Then 5. Then 6. Then 6. 7. 8. Now, 9 is the next smallest, but I can't highlight that because if I do, it'll create this area here. 10. 10's okay. Alright. It looks like every vertex is now connected. Let me just make sure I've got 7 edges. 1, 2, 3, 4, 5, 6, 7. Good, I'm done. So my minimum weight, I'm just going to add these numbers together. 17, 23, 31, 36, 38, 44. Alright, question D. Let's see how many vertices there are. Oh, it looks similar. 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices. So this time we want to be highlighting 8 edges. Okay, smallest. Looks like it's 6. Then 9, 10, 11. I'm not going to highlight this 11 because it's going to create this area. Oh, I forgot about that 8. Let's start again. 6 is the smallest, then 8, then 9, then 10, 11, again, not this 11, not this 12 because it'll create this area. No 13s. 15 is the next smallest, that's fine. No 16s. 17. I can't do this 18 because it'll create this area. I can do this 18. And I think that's it. It looks like every vertex has been connected. Let's just make sure I've got 8 edges. 1, 2, 3, 4, 5, 6, 7, 8. Yep. So now the minimum weight for this is 6 plus 11, 17, 35, 50, 60, 77, 94. Okay, question E. 5 vertices, so we want to be highlighting 4 edges. 9 is the smallest. 9, 10, 10. 18 is the next smallest, but I can't do this one because it'll create this area. Can't do this one because it'll create this area. That one. And that's it. I've done my 4 edges. So minimum weight 20, 38, 47. Okay, question F. There are only 4 vertices here, right? There's no vertex here. I know they cross, but there's no vertex there. So we only want to be highlighting 3 edges. Smallest is 1, then 2, then 4, but I'm not going to highlight 4 because it's going to create this area. So the next one is 5. Minimum weight is 8. Okay. Pause the video, have a go with G and H. Alright, let's have a look. 1, 2, 3, 4, 5, 6, 7, 8 vertices. We want to be highlighting 7 edges. 1, 2, not 3, because then it will create this closed area. 4, 4, 5, 6, 7. That's it. Looks like every vertex is connected. Let's count how many edges. 1, 2, 3, 4, 5, 6, 7. Excellent. So the minimum weight is 3, 10, 20, 29. Question H. 2, 4, 6, 8, 10, 12 vertices. So I'll be highlighting 11 edges. 1, 1, 2, 2, 3, 3, 3, 3, 4. Not this 4, because if I do that, it's going to highlight, it's going to create this closed area here. However, I could have done this 4 instead, but then I can't do this 4 because it will create the same closed area. 5, not that one. Not this, not this. Yes. 6, not that. Yes. And that's it. It looks like I've now connected every vertex. Let's make sure I've got 11 edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So here the minimum weight, let's just add these numbers together. 3, 6, 8, 10, 14, 18, 24. Alright, last 2. Pause the video, have a go with this one yourselves. Okay, let's see how many vertices there are. 1, 2, 3, 4, 5, 6, 7. So we want to be highlighting 6 edges. 1, 2, 3, 4. Okay, I can't highlight this 2 because it's going to create that area. I can't highlight that 2, it's going to create that area. Can do this one though. 2 and 3. Looks like every vertex is now connected. 1, 2, 3, 4, 5, 6 edges. So now the minimum weight is 1, 2, 3, 4 plus 5 is 9. And last one here, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 vertices, so we want to be highlighting 8 edges. 1, 2, and 2. 4, 4. I can't highlight the 6, it's going to create this area. Can't highlight this 7, it's going to create this big area. 7. 8. Can't highlight this 8 because it's going to create this big area here. Or I could have highlighted it but not highlighted this one instead. Right, I could have done that instead. Doesn't matter. And then we've got 9. Looks like everything is connected now. Let's just make sure I've got 8 edges. 1, 2, 3, 4, 5, 6, 7, 8. Good. So the minimum weight is 12, 13, 14, 15, 17, 21, 28, 37. And that's it. So now I hope you know what a tree is, and you know that a spanning tree connects every vertex, and there is no loops or multiple edges or cycles. Pretty much no area that you can color in, no closed areas. If there are n vertices, there is n minus 1 edges. So if there's 100 vertices, there's going to be 99 edges. And I hope now you're familiar and competent in actually identifying what the minimum spanning tree is from a weighted network diagram. Have an awesome day, and I'll see you in the next video. See you.